You've probably looked up at the night sky and seen stars. They look close. They're not. The moon is about 384,000 kilometers away. That already sounds enormous. But the sun? It's about 150 million kilometers from us. Almost 400 times farther than the moon. Now here's where your brain starts to struggle. The nearest star beyond the Sun is called Proxima Centauri. Proxima Centauri is 40 trillion kilometers away. That number is almost meaningless. So scientists use a better unit. They use light years. 1 light year is the distance light travels in 1 full year. Light moves at 300,000 kilometers every second. It can circle Earth 7 times in just 1 second. Even at that incredible speed, light takes 4.24 years to reach Proxima Centauri. That's 4.24 light years away. So the question isn't just, how far is it? The real question is, why is crossing that distance so incredibly difficult? Let's compare with something we've already done. Apollo astronauts traveled to the moon in about 3 days. Our fastest spacecraft, the Voyager 1 probe, has been flying for over 45 years. And it is only 0.002 light-years away. At Voyager's speed, reaching Proxima Centauri would take about 73,000 years. That's longer than all of recorded human history. So our current best technology isn't even close to good enough for interstellar travel. We need something fundamentally different. The core problem is energy. It takes an enormous amount of energy to accelerate something to the speeds needed for interstellar travel. And the faster you want to go, the more fuel you need. But fuel has mass. More mass means you need even more fuel. It's a vicious cycle. Before we explore solutions, we need to understand one rule that applies to everything in the universe. Nothing with mass can travel at the speed of light. This isn't a technology problem. It's a physics law. The closer you get to light speed, the more energy it takes. Infinitely more, right at the limit. So we can't reach light speed. But could we get to, say, 10% of light speed? Or even 20%? That would still make a big difference. At 10% the speed of light, you'd reach Proxima Centauri in roughly 42 years. That's within a human lifetime. That's actually imaginable. So the challenge isn't reach light speed. The challenge is reach a meaningful fraction of light speed, efficiently and safely. Every rocket we've ever launched runs on chemical propulsion. You burn fuel, gas shoots out the back, and the rocket moves forward. This works great for getting to the moon or even Mars. But for interstellar distances, the math just doesn't work. To reach even 10% the speed of light using chemical rockets, you'd need a spacecraft where 99.999% of the total mass is fuel. And that's before you account for slowing down at the destination, which requires the same amount of energy again. Chemical rockets also have a very low exhaust velocity, the speed at which gas leaves the engine. The faster you can eject mass, the more efficient your engine. Chemical reactions release energy at the atomic level. To go interstellar, we need energy from the nucleus of atoms, nuclear energy. Nuclear energy comes in two forms. Fission is splitting heavy atoms apart. Fusion is joining light atoms together. Both release enormous energy. Fission has been used in nuclear power plants and submarines for decades. We understand it well. The idea of fission-powered rockets was seriously studied starting in the 1950s. One real proposal was called Project Orion. The idea was to detonate small nuclear bombs behind a spacecraft, using the explosion to push a massive plate called a pusher plate. Each explosion would be small, timed, and push the plate in a controlled sequence. Hundreds of explosions per minute, each adding velocity. Project Orion's theoretical top speed was around 3 to 10% the speed of light. That's actually within interstellar range. The physics genuinely worked. But there were obvious problems. Launching nuclear bombs in Earth's atmosphere would be catastrophic. So Orion was never built. Fusion is even more powerful than fission. When hydrogen atoms fuse, the energy released per kilogram of fuel is about 10 times greater than fission. A fusion rocket could theoretically reach 10% to 20% of light speed. The exhaust velocity of fusion products is extremely high. The problem? We haven't built a working fusion reactor yet, not even for power plants. Fusion is famously always 30 years away. If fusion is powerful, antimatter is in a completely different league. When matter meets antimatter, they annihilate each other entirely, converting 100% of mass into energy. Einstein's equation E equals mc squared tells us that mass itself is frozen energy. Antimatter annihilation is the most complete way to unlock that energy. 1 gram of antimatter annihilating with 1 gram of matter releases the energy equivalent of a small nuclear bomb. An antimatter rocket could theoretically reach 50% to 70% of the speed of light. That would mean reaching Proxima Centauri in under 10 years. So why aren't we building one? The problem is making antimatter. It takes more energy to produce antimatter than it gives back. And we can only make tiny amounts. At current production rates, it would take millions of years to produce enough antimatter to power an interstellar spacecraft. So antimatter propulsion is real physics, but not yet real engineering. What if we didn't carry fuel at all? What if we used light itself to push us? This is the idea behind solar sails, and it's not science fiction. Light carries momentum. When a photon hits a reflective surface and bounces back, it transfers a tiny push. Add trillions of photons and that push adds up. The Japan Aerospace Exploration Agency launched a real solar sail spacecraft in 2010 called Icaros. It worked. But sunlight weakens with distance. By the time you're past Jupiter, the push is too small to be useful for interstellar speeds. Here's the upgrade. Instead of sunlight, use a powerful laser beam. A laser doesn't spread out like sunlight. It stays focused over vast distances. A project called Breakthrough Starshot proposes using a laser array on Earth or in orbit to push a tiny sailcraft toward Proxima Centauri. The spacecraft would be tiny, roughly the size of a postage stamp. Its sail would be just a few meters wide. Its electronics would weigh just a few grams. The laser array would accelerate this tiny craft to 20% the speed of light in just a few minutes. The laser pushes it, then the craft coasts the rest of the way. At 20% light speed, it would reach Proxima Centauri in about 20 years. The catch is you can't slow it down at the other end. It would fly past in seconds. And the technology challenge is enormous. The laser would need to be powered by a gigawatt of energy, roughly equivalent to a large nuclear power plant running at full capacity just for the launch. What if we stop trying to go fast? What if instead, we built a spacecraft so large and self-contained that people could live their entire lives inside it? This is called a generation ship. The idea is that the first crew would be born, live, and die on the ship. Their children would continue the journey. Their grandchildren would arrive. At even 0.1% the speed of light, a speed we can actually imagine reaching, the journey to Proxima Centauri would take about 4,200 years. 170 generations. That means everyone who started the journey would be gone long before arrival. The people who arrive never knew Earth. They were born in space. The ship would need to be completely self-sustaining. It needs food systems, water recycling, air recycling, energy, medicine, and social structure forever. The hardest problem isn't technical, it's human. Thousands of people in a closed box for thousands of years. The social systems would need to survive wars, rebellions, and cultural drift. Some scientists suggest the minimum viable population to maintain genetic diversity and social stability over thousands of years is around 10,000 to 40,000 people. What if instead of a city ship, we put the crew to sleep for the journey? This idea is called suspended animation, or more broadly, hibernation. The concept is to slow down all biological processes, heartbeat, breathing, metabolism, to near zero. The person doesn't age. The journey feels like a long sleep. We actually see something similar in nature. Some mammals hibernate for months. Their body temperature drops, their heartbeat slows, and they barely age during that time. Scientists at places like SpaceWorks have proposed putting astronauts into a torpor state, similar to medical hypothermia, for months at a time on long missions. The challenge is scaling this from months to thousands of years. There's no evidence any biological system can survive that long in stasis. Not yet. One theoretical solution is to freeze the person at the cellular level, cryonics. Stop all chemical reactions entirely by lowering temperature to near absolute zero. The problem with cryonics is ice crystals. When water freezes inside cells, the crystals puncture and destroy cell membranes. This is still an unsolved problem. Here's something genuinely strange and wonderful. As you travel faster, time itself slows down for you relative to someone who stayed still. This is time dilation. This is a real, measured effect predicted by Einstein's special theory of relativity. It's been confirmed by atomic clocks on aircraft and in satellites. The effect is tiny at everyday speeds. But as you approach the speed of light, it becomes enormous. If a spacecraft travels at 99% the speed of light, time passes 7 times slower on board compared to Earth. At 99.9% of light speed, the factor becomes about 22. At 99.9999%, it's over 700. The traveler barely ages. This means if you could travel at 99.9999% the speed of light, you could cross the entire Milky Way galaxy in your own lifetime. Even though 100,000 years would pass on Earth. The strange part is neither clock is wrong. Time genuinely passes differently based on relative speed. This is not an illusion. It is the nature of space-time. Here's a problem people rarely talk about: space is not perfectly empty. Between stars, there's a thin soup of gas, dust, and particles called the interstellar medium. At slow speeds, these particles are harmless. But at 20% the speed of light, every hydrogen atom you hit carries the energy of a high-velocity bullet. A spacecraft traveling at high speeds would need shielding. The faster it goes, the more radiation and particle impacts it would face, from the front especially. One proposed solution is a magnetic shield, a powerful magnetic field projected in front of the ship to deflect charged particles, similar to how Earth's magnetic field protects us. Neutral particles, ones with no electric charge, wouldn't be deflected by a magnetic field. Those would need a physical shield made of dense material like hydrogen ice. Let's say you successfully launched a probe toward Proxima Centauri. How would you communicate with it during the journey? Radio waves travel at the speed of light. So a signal sent from Earth to a probe near Proxima Centauri takes 4.24 years to arrive. And the response takes another 4.24 years to come back. A conversation would be impossible. You'd send a question, and get an answer 8.5 years later. Any command you send arrives years after the situation has changed. This means any interstellar probe must be highly autonomous. It must make decisions on its own, using artificial intelligence, because there's no time to ask Earth. People have actually designed interstellar spacecraft on paper in serious technical detail. Let's look at some of the most notable ones. Project Daedalus was designed in the 1970s by the British Interplanetary Society. It was a 2-stage fusion rocket designed to reach Barnard's star about 6 light-years away in 50 years. Daedalus would use a fusion reaction fueled by helium-3, a rare isotope found in the outer planets. The craft would be enormous, about 54,000 tons at launch. It was not designed to stop at the destination. Like a flyby mission, it would pass through the target system collecting data and transmitting it back. A one-way scientific probe. Project Longshot was a NASA and U.S. Naval Academy concept from 1987. It proposed a fission-powered probe to Alpha Centauri, arriving in about 100 years. None of these projects were ever funded to construction. But they proved something important. Interstellar travel is not physically impossible. It's an engineering and resource challenge. You've probably heard of warp drives from science fiction. But there's actually a real physics paper behind this idea. In 1994, physicist Miguel Alcubierre proposed a theoretical warp drive. The idea is not to move the spacecraft faster than light. Instead, you compress space-time in front of the ship and expand it behind, effectively moving the region of space the ship sits in. The ship itself is inside a warp bubble. Inside the bubble, everything is normal, no forces, no acceleration felt. The ship moves because space itself moves. Mathematically, this doesn't violate relativity. You're not moving through space faster than light, you're moving space itself, and space has no speed limit. The catch: the original Alcubierre calculation required an amount of exotic negative energy matter roughly equivalent to the mass of Jupiter, with negative mass values. We have no idea if this exists. Revised calculations since then have reduced the requirement significantly. But it still requires exotic matter with properties we've never seen. The warp drive is firmly in the maybe someday category. Another concept from theoretical physics: wormholes. The idea is that space-time can fold, and if 2 points are close together in the fold, you could cut through instead of going around. A wormhole is sometimes called an Einstein-Rosen bridge, proposed theoretically in 1935. It connects 2 separate points in space-time through a tunnel. Wormholes that appear in quantum physics as mathematical solutions are extremely tiny, much smaller than a proton. And they'd collapse almost instantly without some form of exotic matter holding them open. The theoretical solution is the same as with warp drives. Exotic matter with negative energy density could hold a wormhole open and make it large enough to pass through. The scientific consensus right now is that traversable wormholes may be theoretically possible, but no one knows if they can actually exist in the universe. It's an open question. Let's step back and ask a different question. Even if we could travel to another star, which one would we choose? Not all stars are equally promising. The nearest stars to Earth within 15 light-years include Alpha Centauri A and B, Proxima Centauri, Barnard's star, and a handful of red dwarfs. Proxima Centauri is the closest, but it's a red dwarf star, much smaller and cooler than our Sun. It also has violent stellar flares that bombard its planets with radiation. In 2016, astronomers confirmed a planet called Proxima b orbiting Proxima Centauri in the habitable zone. Habitable zone means the distance at which liquid water could exist on a planet's surface. Alpha Centauri is actually a binary star system, 2 stars orbiting each other, with a third companion, Proxima, orbiting much farther out. It's slightly farther than Proxima Centauri alone. Choosing a target requires balancing distance, star stability, planetary candidates, and what science we hope to do. It's a scientific and strategic decision. Here's a question that connects to interstellar travel in a profound way. If intelligent life exists elsewhere in the galaxy, why haven't they visited us? Or at least, why haven't we heard from them? The Milky Way galaxy is about 13 billion years old. If even one civilization became capable of interstellar travel a billion years ago, they could theoretically have colonized the entire galaxy many times over by now. This is the Fermi paradox, named after physicist Enrico Fermi. The galaxy is old, it's big, it has billions of potentially habitable planets. So, where is everybody? One possibility: interstellar travel is so hard that no civilization ever manages it. Maybe we're all stuck in our own solar systems. If that's true, we're more alone than we'd like to believe. Another possibility: interstellar travel takes so long that civilizations don't bother with physical travel, they send information instead. Or maybe civilizations exist but have simply not found us yet. The galaxy is enormous. A signal sent at light speed from one side takes 100,000 years to cross it. Every kilogram you want to send to another star costs enormous amounts of energy. So the question of what to bring, the payload, is critically important. For a small probe, the payload might be scientific instruments, cameras, spectrometers, particle detectors. These can be very light. Breakthrough Starshot's chip payload weighs just a few grams. For a crewed mission, the payload includes humans, life support, food, water, medicine, tools, and enough redundancy to handle anything that goes wrong. That's thousands of tons. Some researchers propose a middle path: send the data for a human, not the human themselves. This is called digital uploading, the idea that a mind could be encoded, transmitted at light speed, and reconstructed. This is speculative and raises enormous philosophical questions. But purely from a physics standpoint, information can travel at light speed, physical humans cannot. It sidesteps the propulsion problem entirely. Let's zoom out and look at the root problem that all these approaches share. It always comes back to energy. Interstellar travel requires more energy than anything we've ever attempted. Let's compare. The entire global energy consumption of humanity in 1 year is about 5 times 10 to the power of 20 joules. A fission rocket to the nearest star would need orders of magnitude more. This is why many scientists believe interstellar travel will require either a fundamentally new energy source, or a complete rethinking of how we define a mission. One interesting path: harvest energy from the star you're passing through. As you approach a star, you could theoretically slingshot around it and steal energy from its gravity. This is called a gravitational assist. We already use this in the solar system. Every major outer planet probe, Voyager, Cassini, New Horizons, used gravitational assists from Jupiter or Saturn to gain speed for free. After all of that, you might ask, is interstellar travel even worth trying? Why spend all this effort just to send a probe to a neighboring star? Because we've found planets. Thousands of them. The Kepler Space Telescope and the TESS mission together have found over 5,500 confirmed exoplanets, with thousands more candidates. Many of these planets are in the habitable zone of their stars. The question, is there life out there, has gone from philosophy to science in just a few decades. If we want to find out whether those planets have life, we ultimately need to go there. Telescopes can only tell us so much from 4 light-years away. Beyond science, there's another reason: survival. If humanity ever spreads beyond one solar system, we're no longer vulnerable to a single catastrophe wiping us all out. Every technological barrier we've described, propulsion, energy, shielding, navigation, is a problem of engineering, not a violation of physics. None of these break any law of nature. That distinction matters enormously. Things that are merely hard can be solved with enough time and resources. Things that are physically impossible cannot. So what would it actually take to make interstellar travel real? Let's build a roadmap, the stepping stones we'd need to reach, in order. Step 1. Build a working fusion reactor. Not just for rockets, for energy on Earth. Fusion would give us essentially unlimited energy, which solves the root problem. Step 2. Develop advanced in-space propulsion. Nuclear thermal engines, fusion drives, or solar electric ion drives could give us far more efficiency than chemical rockets. Step 3. Miniaturize and harden spacecraft electronics. The smaller and more radiation-hardened a probe is, the less fuel it needs and the more robust it becomes. Step 4. Launch an unmanned probe that achieves at least 1% the speed of light. This would be a proof of concept that accelerates something to meaningfully interstellar velocities. Step 5. Send a probe to the nearest star system. Even a flyby, even a tiny chip-sized probe, would be the greatest scientific event in human history. A crewed mission is probably centuries away, if it happens at all. But an unmanned probe to Proxima Centauri within the next 100 years is genuinely plausible. Let's do one final perspective check. Let's shrink the solar system down to a diagram where the distance from Earth to the Sun is just 1 centimeter. On that same scale, where is Proxima Centauri? It would be 272 meters away. That's nearly 3 football fields. And the center of the Milky Way galaxy. On that same scale, it would be 1.7 billion meters away, roughly the distance from Earth to Saturn in real life. When you look at those numbers, interstellar travel stops feeling impossible. It starts feeling like a very long engineering problem, one that enough time and ambition can solve. Here's the thing about exploration: humans have always done it even when it was hard, dangerous, and uncertain. We crossed oceans before we understood them. We climbed mountains before we had the right equipment. We went to the moon before we had reliable computers. The pattern is always the same: curiosity pulls us forward. The stars are the next ocean. The challenges we've talked about today, propulsion, energy, time, are the challenges our descendants will solve the way we solved the challenges of ocean navigation. And the reason to try isn't just science. It's what we might find. If there's life, even microbial life, on a planet around another star, it changes everything about how we understand ourselves. We wouldn't just be sending a probe to another star. We'd be answering the oldest question humans have ever asked: are we alone? Let's bring it all together. The nearest star is 4.24 light-years away. At our fastest current speed, it would take 73,000 years to reach. The main propulsion approaches are nuclear fission pulses, nuclear fusion engines, antimatter rockets, and laser-pushed light sails. Each has different trade-offs. The physics of time dilation means that at high enough speeds, a traveler ages far less than people on Earth. This is real, and it actually helps with long journeys. Space isn't empty. Shielding from particle impacts is a serious engineering challenge that needs to be solved alongside propulsion. Any probe must be autonomous. Communication delays of 8+ years make remote control impossible. AI decision-making is a prerequisite, not an option. The roadmap starts with fusion power, moves to advanced propulsion, shrinking probe designs, and ultimately, an unmanned flyby of Proxima Centauri. Possibly within 100 years. None of this violates any physics. Every challenge is an engineering challenge. The universe doesn't forbid us from doing this. It just makes us work for it. The stars have been waiting 13 billion years. They'll wait a little longer. And one day, maybe not in our lifetime, but in someone's, one of those dots of light will have a ship flying toward it.